Okay, so what we're going to start in with today is ionic compounds, and we're going to do the bonding and the nomenclature portion. And this word nomenclature here is just a fancy way to say formula writing and naming. So it's just a big way to say that. What we're going to focus on today is the bonding part, and the bonding part is really going to re-emphasize all of the electron configuration work we did, all of the valence electron work we did, and then we're going to take all of that and turn it into formulas, and then we're going to take those formulas and we're going to write the names for them. So you're going to, everything we've done for about the past 2 months is going to kind of come together here all at once, and we're going to apply everything. But to start off a little bit at the beginning, we just kind of need to know what a bond is and what does it mean to create a bond. A bond is a force that holds groups of 2 or more atoms together and makes them function as a unit. And so you're going to fill that in right at the very top. You see a little dash beside bond. You're going to fill it in there. And notice you have to have 2 or more atoms. We could also say 2 or more ions in there as well, because when we're doing ionic bonding, what does it sound like we're bringing together? We're bringing the ions together. When we're doing atoms, we're going to be talking about covalent bonding. The formation of the bond occurs in 2 different ways. You can either transfer electrons or you can share electrons between the atomic nuclei. And with ionic bonding, what we're going to see is there's a transfer of electrons going from one type of element over to another type of element. In covalent bonding, there's going to be the sharing occurring. And so what really kind of happens is we have an atom here, and it's got protons, it's got a positive nucleus, and it's got electrons surrounding it. We have another atom over here, and it's got its positive nucleus and its electrons. And what happens is there ends up being something that's known as an electrostatic attraction that occurs. And an electrostatic attraction is just really the big word for positive attracts negative. So what happens is this nucleus is attracted to whose electrons? The blue ones or the green ones? It attracts the green. So there is that positive attracting the negative. But at the same time, the green nucleus is attracting the blue electrons. And so when those opposites attract, that's where we get what's known as electrostatic attraction, and that's just the positive attracting the negative. But we're not going to use, we're not going to use the easy term positive attracting negative. We're going to, make it pre-AP chemistry style and use the proper terminology. And so no matter what kind of bonding's happening, you're always getting this electrostatic attraction in one way or another, positive attracting negative. Now, the 2 types of bonding that we're going to be looking at first refer to intramolecular forces. Now, be careful here because this is intra with an A. We did, before, do you remember when we did intermolecular? Would you remember what intermolecular was? Between what? Between what? between molecules. This is how we got what two phases of matter? Solids and liquids. And that's kind of all we did with the intermolecular forces. Once we get to the end of covalent bonding, you're going to know how to look at a covalently bound molecule and figure out what intermolecular forces it would use to stay together as a solid or a liquid. Well, the intra are what you need before you can get to the inter. The intra gets the atoms or the ions to stick together. And that's where we have our two different types. We have our covalent or our ionic. Now, they're very simple to recognize the difference between these two. The covalent holds only nonmetals together. So you're working with a very small portion of your periodic table. You just have this little area over here and hydrogen. So it doesn't work with a whole lot of atoms. The ionic encompasses everything on the periodic table because you have to take one metal, put it with one nonmetal in order to create the ionic compound. And my little trick to remember this, intra has an A in it and it holds atoms together. So hopefully that'll let you connect those two pieces together. So as we start talking about this bond and transferring electrons, the next important thing to figure out is there are a lot of electrons. There on the periodic table, there are 118 electrons. Which ones are we going to use? We're just hearing crickets. I should get a little cricket sound player so they can hear the crickets. Core electrons or valence electrons? Valence electrons, because remember, that's why we did the whole Lewis dot diagram, because that showed us what our valence electrons were, because that was going to tell which ones could be used for bonding. So what electrons and how are we going to make this work? The valence electrons are used for bonding. Where do we find our valence electrons? What sublevel? Valence electrons, where they're in the outermost principal energy level, but what two sublevels can they be in? They can be in the S and the P. They're S and P sublevels. So what's the maximum number of valence electrons you could have? You could have 8 valence electrons. And that 8 is very important because 8 happens to be the number of valence electrons that the noble gases have. And having those 8 valence electrons makes for a really stable atom, because then everything's completely filled. That's giving us our lowest energy potential. And so everybody wants to be a noble gas. They're kind of the cool kids on the periodic table. Everybody wants to bond so they can achieve that noble gas configuration. And now this is kind of the stuff we've already talked about before. If the element is a metal, it wants to achieve the noble gas configuration for the noble gas before. The reason it's the noble gas before is because it loses valence electrons. So it's dropping back to a lesser number of total electrons. And remember, these are called cations. How do we remember that cations are positive? It has the plus sign right in the middle of it to help us remember. In our ionic compound, we have to put that with the nonmetal. And this works out really well because what happens is the metals lose the electrons. Well, it needs to pair with something that's going to pick those electrons up in order to obey the law of conservation of mass. So the nonmetals gain electrons to achieve this. So what happens is they go to the noble gas that's past them, and that's because they gain valence electrons in order to make that happen. And as we go through and do our work today where we are writing our electron configurations, we're going to get some more practice with writing the regular electron configuration and then showing how it becomes an ion, because I think that was a small weakness on your last assessment. By the end of today, you should probably have that down really good and understand what's happening there. Okay, so for ionic bonding, this occurs in ionic compounds which contain a metal and a non-metal. What does our metal act as? What kind of ion? It's our cation. And the non-metal is our anion. The reason it's called ionic bonding is because you have to take two ions and put them together. So you have to find your cation and your anion in order to make that happen. Well, this works well because our metals are atoms that lose their valence electrons relatively easy. And as we progress through periodic trends and things like that, we'll see that because of their makeup with their protons and their core electrons, that leads to them losing their electrons very, very easily. Well, what we do is react them with the nonmetals, and the nonmetals have a high affinity for electrons. What does affinity mean? Not infinity, but affinity. Attraction or love for electrons, and that has to do with what's happening in their nucleus and with their core electrons. So this is really a match made in heaven, taking metals and putting them with nonmetals. Once again, every time it is a transfer of electrons. And every form of bonding, whether it's ionic or covalent, comes from that electrostatic attraction. And so what happens here are we take electrons from our metals, pack them up, move them over, they go to the nonmetals. When the metals lose, they end up positive. When the nonmetals gain, they end up with negative. Opposites attract, and we are able to create a bond. Any questions so far? Affinity is attraction or love. I have an affinity for Five Guys French fries. Okay, so these next couple slides I'm actually going to speed through because this is stuff that I sometimes teach first years, but we're going to skip it this year. It's AP material. You'll never see it on an SOL test. So don't panic. Oh yeah, it's not even in your packet. Now, I've created this packet, and then I thought about it, and I've decided I'm going to teach this from a slightly different perspective this year to work on some skill development that I think we might need. So this particular slide is not in your PowerPoint. So what I want you to do is take the first page that we just filled out, turn it over, the back is blank, and you can write it on the back. because I'm going to do creating our ionic compounds in a little bit different way this year. It's all going to be based off of electron configurations, finding valence electrons, and figuring out how much they either need to gain or lose in order to create a noble gas configuration. So a lot of this is going to just be practicing skills that we've been working on before. The first thing we're going to want to do as we are creating these these ionic compounds is we want to write an electron configuration for both the metal and the non-metal atom. And we already know how to do that, right? Say something so they think I'm not in here talking to myself. So we're going to practice that again. Now, the part that I think we're a little bit unsure on is how to turn those atoms into ions. And I noticed that was a little bit sketchy on your assessment from last Friday. I'm almost done grading them. I've noticed a little few missteps. So we're going to go over that again today, so we should have that down today. And then this final step really isn't going to make a whole lot of sense until I actually work through a problem, and then you'll easily see what's going on. So just write it down for now. Determine how many of each are necessary to have the charges add up to 0. And this is going to be a common theme throughout all of our work with ionic compounds, whether we're trying to figure out what the structure would look like, or if we're trying to figure out what the formula would be, or if we're working on the name. This last step, you know, the idea of 0 is going to be very important. You always want your positive to equal your negative, much like if we were dealing with atoms. Back when we started, like in November, with atomic structure, and we were trying, you know, we did those charts where they had protons, electrons, and neutrons in them. They were always atoms, so our protons always equaled our electrons. So trying to keep that balanced here again. So I want to do 3 examples for you, showing you exactly what work I expect to see and showing you how these electrons get moved about. Now, I need John to get his head up. I need Vincent to not fall asleep. You're drifting there. If you need to stand up for a second, you can. That might be a good idea if you need to get a drink of water. But we're not taking a break because I'm taping. So you're going to have to wait. No, we're on a roll. We're going to keep going. Okay. So we're going to create some ionic compounds here. So I'm actually going to start with one that I actually have a model of. Emily, you need to leave now. And so we're going to I have a model up here of table salt. And so what we're going to do is we're going to work through the process that would show us that this is what it's going to become. So first off, let's have sodium on one side, chlorine on the other. Make sure you got your periodic table out where you can see it easily. Should be front and center. Is sodium a metal or a non-metal? It's a metal. And do metals like to gain electrons or lose electrons? Lose. Okay. chlorine, therefore, if we're going to put these two things together in ionic bond, chlorine has to be a what? Nonmetal. And it does what with electrons? Gains. Okay, so we're going to start these pretty much like the other work we've been doing recently. We're going to start off with how many protons and electrons does the sodium atom have? It's not up here on my face, it's right here. 11 protons and 11 electrons. Because it's the atom, it is neutral. These two things have to be equal. What about chlorine? 17 for both. 17 protons and 17 electrons. So the very first thing we're going to do is we're going to write the electron configurations for this. So, electron configuration for sodium is what? 1s2, 2s2, 2p6, 3s1. Remember, it's right there on your periodic table, so you don't have to guess. What about chlorine? 1s2, 2s2, 2p6, 3s2, and 3p5. So that's exactly what we've done before, right? Okay. So the next thing we're going to do is mark our valence electrons. And in sodium, what's our valence shell? 3. So we're going to circle our 3s1. What's our valence shell over in chlorine? Now, it's not just 3p5, it's also 3s2. Remember, if you ever circle a p, you have to go find the s to go along with it. When you circle the p, there has to be an s. So, sodium right now has how many valence electrons? It only has one valence electron. And in order to achieve its 8 valence electrons, is it easier for it to lose that one or gain 7 more? Lose 1. And if you notice, that's why metals always lose, because they typically have 4 or less valence electrons, and so it's always easier for them to lose those small number of valence electrons instead of trying to add a much larger number of valence electrons. So here we're going to lose 1 valence electron. And before, when we were doing our atoms and ions, we didn't really think about where that electron was going to go, but it has to go somewhere. You have to obey the law of conservation of mass. An electron is matter. It can't be just destroyed and lost. It has to go somewhere. Well, when you look at chlorine, how many valence electrons does it have? It has 7. To get to an octet, it needs 1. So over here, we need to gain 1 valence electron. Well, this kind of looks like perfection, right? Sodium has 1 to get rid of. Chlorine needs 1 in order, so it's kind of a match made in heaven. They're not always this perfect, so I'll do a couple examples where they don't work out this perfectly, and so you can see what you need to do. So now as we go down, now we want to figure out what happened now when we look at the ion. So now when we write the new electron configuration, what are we going to leave off? We're going to leave off the 3s1, so 1s2, 2s2, 2p6. We still have 11 protons, right? Right, we never changed protons. What did we do to our electrons? Lost 1, so now we have 10 electrons. Do we need a greater than, less than, or equal in there? We need a greater than, because our protons are greater than our electrons. Well, what does that tell you about this charge of this ion? It's positive by how many? 1. It's a +1. Positive because we have a larger number of protons and we have exactly one more proton, which makes it +1. We go over to chlorine. 1s2, 2s2, 2p6, 3s2. What are we going to do to that last part? We're going to make it 3p6. We still have 17 protons, right? But what did we do to our electrons? Now they are more, 18. Greater than, less than, or equal sign in here? Less than. So what charge do we end up on with this one? -1, because its electrons are bigger, so that's why we have a negative number. Malcolm, hit him. And we're greater by 1, so that's why it's -1. Now, is this a noble gas configuration? Which noble gas? Neon, okay. Is that one a noble gas configuration? Yes, it is argon. And so that's what's always going to happen in the formation of these ions is you have to achieve a noble gas configuration because that's where you have your octet. Our new valence shell is what here on sodium? 2s2, 2p6. So there we have 8 valence electrons. And over here, now we have 3s2, 3p6, so we have 8 valence electrons. So now, questions up to this point, because this is pretty much review. The new part is how do we actually put this together and make a formula for sodium chloride? Well, now we know what forms we're going to be using. We're going to be using a sodium ion that's +1 and a chloride ion that's -1. So we're going to put a sodium +1 with a chlorine -1 to create the formula. Now that last step said what had to be true? The charges have to add up to 0. If we take +1 plus a -1, do we get 0? Yes. Now, why is this holding together? Why are these holding together? Nope. Nope. Because we have a positive here and a negative here, and that is called what? Electrostatic something. Electrostatic attraction. Electrostatic attraction. And so what I have here, so if I pull just 2 of these off, 1 formula unit of sodium chloride, that's exactly what I have here. This is 1 formula unit of sodium chloride, and notice they're sticking together. Well, these have really good magnets in them, and what we have done here is we've put the one pole of the magnet is on all of these is facing out. The opposite pole, so here maybe the positive pole is showing, here the negative pole is showing, and so when you put them together, they form a bond. Now, what happens if I try and take negative to negative? Yeah, and I want to pass it because you can actually feel it. And so attraction and repulsion are sometimes a hard concept for you to, especially the repulsion. So I was thinking if you could actually try and now you want to make sure you line the silver to the silver. Try and put those together and notice you can actually feel it pushing it apart. You can't push it together. So what happens is a lot of the sodiums and the chlorides, they come together in ionic compounds. They make very uniform lattice structures. This is highly organized, isn't it? Every way I turn it, it looks exactly the same. No matter how I turn it, if you look inside, you can see it's very highly organized. That's how all ionic compounds are. They're super boring because they don't make really any fun shapes. When we get into covalent, that's where we'll get into bent molecules and tetrahedral molecules, and maybe we'll do a little octahedral, and we get these very interesting, unique shapes. But this is cool because you can pull it apart and feel the actual repulsion. I could even put, it wouldn't do this because that's not organized. It likes to be organized. Okay, so I want to do two more examples, which are what happens when it's not perfect. What happens when I need to lose 2 valence electrons here and I need to gain 4 valence electrons? What happens when it's not a perfect match? I'll show you what to do with that. So we're still going to use sodium. Because I want you to see that sodium can bond with lots of different things. But we're going to switch out, instead of chlorine, we're going to put oxygen in instead. So sodium there, chlorine there. We already know that sodium has 11 protons and yeah, could somebody please stop me before I do this? I didn't hear you. Sorry. I'm up here in La La Land. I didn't. Oxygen, 8. 8 protons, 8 electrons. So we know this electron configuration: 1s2, 2s2, 2p6, 3s1. We need to write the electron configuration for oxygen. So somebody read it off to me. Okay, Matthew, sodium, valence shell, 3. So, Matthew, how many electrons is it going to gain or lose? Lose 1. Okay. Sydney. In oxygen, what's the valence shell? And what am I going to circle? We're going to circle both of them. How many valence electrons does that give me? 6. So how many is it going to gain or lose? Gain 2. So this doesn't look as neat as the last one, because on the last one, we were going to lose 1, gain 1, easy problem. We're not going to change anything we're going to do. We're going to go through the making. Now we know this is going to lose 1, we're going to make it into its ion. This one needs to gain 2, we're going to make it into its ion. At the last step, I'll show you how it all works out, how we actually do gain and lose an equal number of electrons. So for sodium, we already found out it's what charge? What was it last time? Positive 1. 11 protons is greater than 10 electrons. And we lost our 1. Now when we come to oxygen, 1s2, 2s2, what am I going to finish it with? 2p6. I'm going to add 2 in. I'm going to have 2p6. That still gives me 8 protons, but how many electrons do I have now? We've added 2 more in. And you can always check your new electron configuration and add up the superscripts. Do I need a greater than, less than, or equal to? Less than. So is oxygen going to be positive or negative? Negative by how much? 2, because I have more electrons, which makes it negative, and I have more by 2, which makes it negative 2. Did both of these reach a noble gas? Yes. And where's the octet in both of them? The second principal energy level. If we mark this and this, 2 plus 2 gives us 8. And over here, there we have 8 as well. Was that okay? Oh. 6 is 8. So last thing we want to do is put this together. So sodium is plus 1. Oxygen is minus 2. Does that add up to 0? No. And in an ionic compound, they have to add up to 0. And so what we're going to do is it's known as the crisscross. It's very easy. We're going to take our charges, the numbers, and we're going to crisscross them down to become subscripts. So the 1 would go here, and the 2 would go there. Now, the one thing we don't do is we don't write 1s. They're going to leave this blank. Never write. I'm just losing my mind here. Never write a 1. And so now to check out that, yes, mathematically this adds up to 0. 2 times positive 1 is positive 2. 2 times positive 1 is positive 2. Plus our negative 2 equals 0. It's kind of like you don't typically write 1x1 in algebra. It's the same thing here. So when we don't write 1s as subscripts, we don't write 1s when we balance equations. They're understood. Yeah. So in order to properly form this compound, in order to make this compound happen, how many sodiums do we actually have to have? You have to have 2, because each sodium can only give how many electrons? 1, and oxygen needs 2. So now as you start to think about maybe formulas you've seen before and you see those subscripts, the reason those subscripts are popping up is because in order to create the bond and give everything 8 valence electrons and it's octet, you need different numbers sometimes. So let me show you one last one, and then the rest of the class period will be practice for you. So one last example. And we're going to do aluminum and sulfur. How many protons does aluminum have? 13. So we've got 13 protons and 13 electrons. Sulfur has how many protons? 16 protons and 16 electrons. Okay, Michelle, will you give me the electron configuration for aluminum? P1. Okay, and John, could you give me the electron configuration for sulfur?
1s2, 2s2, 2p6, 3s2, 3p.
Okay, Jess. In aluminum, what is the valence shell? What should I circle?
3s2.
Okay, 3s2 and 3p1. Wilbert, in sulfur, 3s2, 3p4. Okay, Tori, how many valence electrons does aluminum need to gain or lose? Loses 3. We need to lose 3 valence electrons. Anybody in sulfur, does it need to gain or lose valence electrons? Gain how many? Gain 2. Well, this really doesn't appear like it's going to work very well in this case, but I'll show you. It'll all work out. It's into a nice, neat package. Let's go to aluminum. And when I write its electron configuration, where am I going to stop? 2p6. So I need to lose all of that I've circled in red. So we have still 13 protons, but what do we do to electrons now? There are 10. Greater than, less than, or equal to? Greater than. Over to, charge. Positive what? 3. Positive because there's more protons. 3 because there's 3 more protons than there are electrons. Okay, sulfur. What am I going to do to write its electron configuration? Make 3p4 into 3p6. So we still have 16 protons, but how many electrons do we have now? 18. Greater than, less than, or equal to, what do we need in there? Less than. And what's our charge? -2. minus because there's more electrons, 2 because there's 2 more electrons than protons. Did we get our noble gases? Yes. Anytime you end up at P6, you know you're at a noble gas. Our octet here is our 2s2, 2p6. What is it over in our sulfur? 3s2, 3p6. Okay, so coming down to what is it going to take to put this thing together? Because obviously one aluminum and one sulfur is not going to work because they don't have an equal number of electrons being gained and lost. So we go to aluminum and sulfur plus 3 minus 2. Does this add up to 0? No. So we're going to do the crisscross. We'll bring a 2 down to aluminum. You can't have any charges down there, just bringing the number. And what does sulfur get? It gets a 3. 2 times positive 3 is positive 6, plus 3 times negative 2 is negative 6. That equals 0. And so what happens, we use 2 aluminums. 2 aluminums lose a total of how many electrons? 6. The 3 sulfurs, they gain a total of how many electrons? They gain 6. And so sometimes what you can kind of do is look up here and see where you might be going if you do the least common multiple between the loss and the gain. Did you figure that out, Jordan? Oh, it looked like you were. It looked like you're going. See, I told you. I knew. Oh, and don't forget, I always want you to write something down here about the electrostatic attraction. And it can be just as simple as writing the 2 words, so I know you know why these things happen. Okay, let me escape out of here and stop this.